Where there is life, there's also light. If we look at our cities at night, we see light everywhere. But not only in the streets, but also in our pockets, with our smartphones, their displays, with our smart watches, with the smart gadgets that we carry all around us. But also in our homes, with our LED lights. In all of these applications, materials and molecules are getting excited by electrical energy, and when they return to their ground state, they emit this energy in the form of light. Human life on our planet is so tightly associated with light that a modern society would not be thinkable without light and light-emitting materials. And what is true for us as humans and as a human society is also true for nature. Where there is life, there's also light. Bioluminescence, the phenomenon where you have, during a chemical reaction within a biological organism, light emission, has evolved more than 50 times independently within the course of evolution. It's a true success model of efficient light generation in nature. There are more than 3,000 species known which are able to show bioluminescence. And today we think that bioluminescence first appeared around 2.5 billion years ago when oxygen first came into our Earth's atmosphere. And during this time the organisms needed a way to detoxify this oxygen, and one form was to use it for some biochemical reaction, and as a side product they created light. The fireflies that we know all, they started to glow around 120 million years ago, and since that time there's a gradual uphill trend in efficiency and also color modulation. And you know bioluminescence probably also from the movies, like Life of Pi or the different Avatar movies you probably know. And within these movies you see, for instance, a protagonist in a large sea full of bioluminescent jellyfish, or some bioluminescent fungi in Avatar, some bioluminescent glowing and flying creatures. So is this what you see there in the movies pure science fiction, or is there maybe a glimpse of reality also in there? And to illustrate this, I brought you this satellite composite image. It shows the east coast of Africa. Here on the east coast you see a small luminescent spot, but it's not small at all. If we put as a reference the map of Germany next to it, we see it's more than 400 kilometers long. So imagine you are on a boat in the middle of this luminescent spot. You would probably see, like in the movies, an ocean full of bioluminescence. Yeah, what is happening here? We see the reaction of a molecule in a small algae called dinoflagellate. In these areas, these algae are blooming very intensively, and in there a molecule called luciferin is oxidized with an enzyme called luciferase together with oxygen, and it produces an oxidized form of the luciferin called oxyluciferin in the excited state. And when this molecule releases its energy to the ground state, it emits light. But we don't have to travel so far to the east coast of Africa. We can also see this in our forests here in Germany. Here I brought you a small fungus that you can find almost everywhere. It's Panellus stipicus, the herbe Zwergknäuling. You can find this on old birch stumps, and when you look at it at night, it looks like this. It glows green. And what is happening here is the oxidation of a derivative of caffeic acid. Caffeic acid, a molecule we all know from our daily coffee. And the funguses there have certain enzymes that can catalyze its reaction, and during this oxidation again we see the emission of light. And when scientists understood the intricate biochemical reactions here for the first time, they clonated this system into other plants and made them also bioluminescent. And so the startup Light Bio from the US from the US made the first artificial bioluminescent plant, a Petumia, and they are now selling it in the US, and Time magazine thought in 2024 that this was one of the greatest inventions of the year. But we all know probably best from our own experience firefly. Now, when we go out at night, typically in late May, early June, just after sunset, we see meadows full of bioluminescent firefly. And this is actually one of the best studied bioluminescent systems so far. In fireflies, the ecological function of the bioluminescence is mainly for mate attractions. And so scientists studied this system already in the 50s and the 60s of the last century. They collected a large variety of specimens, around 15 to 20,000 fireflies, with the help of the local community, and extracted the molecules that they found in the abdominal part of these organisms. And in the course of several years of research, they came up with a mechanism to actually explain the bioluminescent reaction that happens there in quite detail. And don't worry, I will not go into the very detail of this very intricate mechanism, but I would like to highlight 2 points here. First, the light emission in this process is very efficient, with a quantum yield of about 41%. This is more efficient than all the OLEDs and all the displays that we have now commercially applied. And the second thing is, it's a closed loop system, meaning that the reaction product that is formed in this reaction can get reused again to run the reaction over and over and over again. So how can we now use this knowledge to actually engineer new materials for displays and beyond? For this, we first need to understand how an OLED works. The OLED that powers your very smartphone that you probably have in your pocket. An OLED is comprised of many, many different layers, but in the middle of it, the magic is happening. In the so-called EML, the emissive layer, charges recombine and excite electronically molecules into their excited state. And this enables so many nice applications that we find now of these technologies, making bendable, rollable, transparent displays even. So researchers wondered quite early, how can we translate the knowledge from bioluminescence to the design of new OLEDs? The first idea that they had here was actually not looking at the molecules in firefly, but just at the structure, the abdominal structure of firefly. Because at its outer surface, when you zoom in with a very good microscope, you see a scale-like pattern that is stacked on top of each other. And this can create an interference phenomena which actually helps outcouple the light from the bioluminescence reaction, increasing the overall efficiency. And when scientists applied similar patterns to the surface of OLED, they found again an increase in efficiency. But there's a much larger problem within the OLED technology, and that's a sustainability problem. There are increasing reports now that find OLED materials in wildlife and even in human breast milk. They are tuned for maximum stability, and we believe that they might bioaccumulate, so don't degrade when they come into an environment. So now, can we use the knowledge that we acquire from studying bioluminescent systems to solve these problems? And I say yes, we can do this by engineering so-called biolamps, which are bio-inspired organic light-emitting materials. So combining OLED materials with green chemistry to have sustainable light-emitting materials. And to illustrate this, I would like to show you here a couple of the structures that we actually find in all these bioluminescent organisms. There's a vast structural diversity that we can use for inspiration here. And since firefly are the organisms that best studied, we also know their precise color modulating mechanism, because there are several insects that use the same bioluminescent system, so the same light emitter, but they all emit across the optical spectrum from blue teal to orange red, just by changing certain properties of the molecule and its photophysical properties. And after we understood this, we were able to engineer materials that are inspired by the firefly luciferin to emit over the entire optical spectrum, from blue to red and even white light emission that we can do with this. And our future vision is now to use these materials to build bio-inspired OLEDs, which we call bio-OLED. And what shall the bio-OLED do? Well, it should ideally combine the positive properties of OLEDs and the classical OLED materials with the sustainability aspects of bioluminescence, mainly that it's metal-free, that it's biodegradable, and that it shows low bioaccumulation. And we hope that the bio-OLED can combine this. But we also would like to go beyond. In our laboratory in Dresden, we study with the help of the Free State of Saxony and funding by the European Union within the research network Biotronus, also other applications of such bio-inspired materials, namely in the field of bioelectronics. I would like to show you two examples for this. One would be smart packaging materials. Imagine you go to your supermarket and you would like to buy a piece of meat, but you don't really know if it's fresh. It certainly has a due date, but is it really fresh or is it just printed on there that it's fresh? Well, we can sense certain pH changes, for instance, with our materials and give an indication if the meat is still fresh or not. If the label is white, you see good meat. If the label gets red, well, the meat is spoiled and you better should not eat it. But we can also use this for instance, medical sensing applications, developing biodegradable capsules, which we would want to use in the future to sense, for instance, also bacterial contamination that you have in your body. And you don't need to swallow a large endoscope anymore, you just swallow this pill. It senses in your stomach the contamination of the materials and then biodegrades. You don't need to remove it anymore. And with this research, we want to contribute to a future that looks less like an industrial wasteland, but more like a vibrantly glowing ecosystem. Because after all, where there's life, there's also light.